Well, it is now 11 o'clock, so we're going to start this is our 9th field trip online from Tule ponds at Tyson's Lagoon. Again, my name is Dr. Joyce Bluford. Most kids call me Dr. Joyce, and I'll be your host at the beginning, and Debbie Davidson from North Carolina will be doing the end part, but she's live here in California. So we're going to now, let's see. Our topic today is giving water a second chance. First, we're going to explain why water is so important and why it acts the way it does in the real world. Now, what you see there is a picture of a watershed. Now, a watershed has kind of like it's where water goes down into a central area. So there's many, many watersheds. Here in the San Francisco Bay, there's one huge watershed. That would be the San Francisco Bay watershed, all the creeks that go into it. And then you have a lot of little ones, like we're here in the Maui Slough watershed because our water at Tule Ponds eventually goes down to what we call the Maui Slough. But we want to understand how that works and how it's so important how that water is actually cleaned. Now, I have a model in front of me. This is something that you can do at home with just dirt. You can get something. This is a substance called Shape It. Now, whenever you start building a city, you have to think about one thing, and that's gravity. Gravity is basically what controls how water flows on the continent. It is every drop of water's dream to go to sea level. It's just the way it goes. Now, you can illustrate this very easily. Here in the Bay Area, we have a lot of hills, and so we have to be real careful where we put cities. Now, if I put and this represents a water drop, and we're going to just let it go. Now notice, it goes down into the end of the watershed. But can humans control water? Well, if we go like that, it didn't go. So this is acting as a little dam. So if we want to save water, because we all need water to live, that we need to dam water sometimes so we can then use it as drinking water. But let's say you have a lot of raindrops coming. What happens? Whoop. So we have an activity for kids that they have to make dams, they have to make water flow. Now, especially like in places like San Francisco where you have it very hilly and you have a lot of homes, all of their stormwater, so when it rains, it has to go through another system so it doesn't make sinkholes and things would collapse. Here in Fremont, in the TriCity area, in parts of going up toward Oakland, we do have creeks, and so our stormwater can go to the creeks and out the watershed. So we have to make sure our watershed is clean. So this is one of our activities. Let me put this down for a second so I can easily get. Okay, so now what's so important about water? Well, water is, it's what we call the universal solvent. Most things can dissolve in it. That's why we have salt water, so it's H2O, which is hydrogen and oxygen, and things can get dissolved in it, like salt, sodium chloride. So if you look at this little model here, it looks like a little teddy bear, and we'll show you some activities you can do to kind of remember this. That little molecule of water is the weirdest compound known to humans. It can go through 3 states of matter on surface conditions. So it can be ice, solid, it can be steam, which would be gas, and it could be the liquid, which most people think of H2O. But its bond is so strong, almost anything can be dissolved in it. So, and another thing that we're going to look at today, because gravity, as I mentioned before, is important, but there's another thing called surface tension. Now, surface tension is when the molecules tend to hold hands very tight, and they let things like geese float. It allows things to actually stay on top of the water. Sometimes if you break the surface tension, things will fall in, like little bugs do that. We'll see how biological life has adapted to it. So, and then the most important thing about water is all life requires water. We can live for a longer time without food, but we cannot with water, because then our body starts breaking down. Water is the most important molecule we have. Now let's take a look at the surface tension here. Now, one of the neat things about water is that it can defy gravity. What? What does that mean? Well, defying gravity means that, like when you have a tree, remember when we talked about the trees early on in the series, trees need water. And so the water have to go up the roots and then to the leaves. And so it's all about this surface tension. So if you look over here on this, where it says surface of water, you'll notice that there's water, that there is these molecules of H2O crawling up. So it actually can walk up. It's just the nature of this H2O molecule. Now, if you look at that upper right-hand corner picture, you'll notice that the molecules on the surface all are holding together. So it makes the surface stronger. So that's why a bug, like a water strider or an insect, can go on the surface of the water. You can see how it's almost pushing down so it stays up. Surface tension is also a reason why we have bubbles. And Debbie is going to do a whole thing on bubbles later on to show you why bubbles are always what shape. You'll find that out later on. Now also, if you look at a water drop coming from the sink and you just let one drop go, it will start like it's attached to the faucet, and then it'll be spherical. So with that, this is a little experiment you can do at home. Everybody uses water, but do you look at water? Let's take a look.
Let's look at a drop of water. If you notice, as it comes down, it's no longer a stream, it's free falling, and gravity and surface tension makes it into like a little ball, like a drip. Now as you go down, you'll notice that not all of it goes in the water, but let's look at how they form, and as they get large enough, the surface tension is broken, and then it flows out.
Okay, so this is how surface tension, when you really look at how water moves, it's really interesting spending times. And you've probably seen, if you have a cat will play with the water. You think he's observing? Probably. Now let's take a look at the strength of that surface water. So let's look at this little picture. This is a recent one. This is a Canada geese with her 4 babies, is that? Now notice the stream of, they've broken, and you see these waves. That's actually for another class to understand that interference there. But notice that it's important for these big creatures to float up on the top. Okay, now let's take a look at, so surface tension is important, and gravity also helps this water to move. Let's take a look at what gravity does and how surface tension kind of holds it back and forms these patterns. So this is here at Tule ponds. So you can almost see how the gravity is flowing downward. So a city has to, when they design cities, gravity is very, because most things are gravity fed. We're going to find out even cleaning our poop and our sewer system requires gravity. Gravity is very important for water as it's moving around. So let's take another picture or a little video of water moving from Tule ponds. As I had mentioned in earlier ones, Tule ponds is a stormwater remediation area. So this is preventing parts of Fremont from flooding. So the water will stay here for a while, and then we'll go through a series of channels and go to the end of the watershed, which here would be Maori Slough. Now, first I want to read you a little story called Giving Water a Second Chance. This is trying to explain that that water that's dripping from the faucet or any kind of water that goes from the toilet can be reused. And we're going to see how a lot of agencies, every city has a different type of agencies. Like we here have Alameda County Water District, takes care of the drinking water. Union Sanitary District takes care of our sewage, and the county takes care of stormwater in the Tri-City area. It's different in different places, and we'll go over that later. But here is Giving Water a Second Chance.
Giving Water a Second Chance, written by Joyce Bluford, illustrated by Augustine Salgado, animated by Doris Rea and Hagos Tavolti. This is a story about how water changes and can be dirty and then get cleaned. Dippy Drippy Drop sat on a rock in a nearby bay. Notice that water is in two forms on Earth, one as fresh water and the majority of it as marine water or salty water. Dippy Drippy Drop was thinking about his family and was sad. He began to dream about Beady Bead and Cloudy. He started to cry. One of his tears came alive. Dippy, said Beady Bee, I'll come back to share some water adventures with you. Oh, Beady, said Dippy, it is always fun to go through the water cycle with you, as we have done over and over again. Notice Beady and Dippy are going through precipitation, evaporation, condensation over and over again. Remember the first time we became water? Mother Hydrogen and Father Oxygen gave birth to us in a volcano. We were just gas then and floated up into the sky and met Cloudy. I have to explain this a little bit. The Earth, which is about 3.5 to 4 billion years old, did not have water. It was the miracle of volcanoes that what we called outgassed enough energy to bind hydrogen and oxygen together to give us water over time. It took about 1 billion years before there was even enough water to start thinking about why water was important to our Earth. We played on Cloudy's belly. Life was fun, but it became crowded with too many drops. We had to leave. Dippy became a snowflake and Beady became rain. They met Wanda Wet, their cousin, who came down as hail. They all finally landed in rivers and were proud to become part of the Earth's water supply. A long time ago, a dinosaur drank Dippy. Dippy had a wild ride through the dinosaur, then sank through the rocks into groundwater and then into a stream. Want to explain this a little bit. Water recycles throughout billions of years. So a water droplet that might have been part of a dinosaur's wee-wee could have been cleaned, and you could be drinking that today. Wanda Wet became part of a lake that was very muddy. She evaporated and met Cloudy. Then she fell back to Earth as a clean raindrop. Just so you understand, when you get muddy or dirty, the only clean H2O will evaporate into the sky. Dippy and Wanda were clean naturally through the water cycle. People could now drink Dippy and Wanda after they were cleaned by nature. Once Beady got cleaned a different way. Beady belonged to a dirty water gang. She was sent to a cleaning factory, which removed big clumps of dirt.
Beatty needed a second cleaning before she was clean enough to use again. Although Beatty was cleaned by a factory, some of her family was cleaned by nature. Now all were clean and ready to be used. Recycled Beatty could be used to make flowers and vegetables grow. Recycled Beatty could also be found swimming in a toilet bowl or keeping the grass green at your local park. The water is clean and will not harm any living creatures. Dippy, Wanda, Beatty, and Cloudy were so happy they could be recycled over and over to help people, animals, and plants live on the planet Earth. The end of this story, but not of the water cycle, which goes on
So
and
let's take a
on
look at
and
how
on.
cleaning water, how you actually do it in our area. As I mentioned, Tule ponds filters water, storm water, and we call that bioremediation. We have things called Tules that have this miraculous ability to take out heavy metals out of stormwater. And so when water comes through here, biology does its magic and takes out some of the bad things that might go into the San Francisco Bay. So stormwater needs to be, a lot of it is not filtered, but here the county of Alameda County decided that this was a great way. So if you look at the map at Tule Ponds, the way it goes is the top pond here, these are what we call constructed wetlands. Water goes into pond A, then to B, then to C, and then goes out to the big lagoon called Tyson's Lagoon. And then it goes out into what we call storm drains. The other way to clean water is through water districts. So that's our drinking water. We do not drink storm water, only drinking water, and we'll go a little over how that happens. And then of course, every city needs to have water or sewage water or that contains our poop, that has to be cleaned too before it goes out into the bay. And then we're also going to find out that we make products of it. Just think, guys, back 1972, I know that seems a long time to most of you, but 1972, your parents, well, most of your parents weren't born then, but your grandparents definitely were. This is where they used to just put in raw sewage into the San Francisco Bay, and it was dirty and stinky. Now, this is our area right here. Now, Tule Pond, you can see the word Newark, Fremont, and then if you right above Fremont, you see a little kind of like area coming in here. This is Tule Ponds. That's a natural lake. It's been here for over 4,000 years that we know of. And then we have Lake Elizabeth, which is right just south of it. Then you have the Mission Creek coming down. And so all of the, if you notice, it goes from the hills out to the San Francisco Bay. Now, our watershed here is called Alameda Creek watershed. And this is a very important watershed, which I'll talk a little bit about later. So the bright blue is stormwater or groundwater or water that is going from creeks. Now, we also have the brown lines, and that's what we call our poop lines. And that is where our poop travels in order to get cleaned. Now remember, gravity has to be pulling it. And so all of our poopy water needs to go to this in Union City. That's the poop cleaning machine over in this area, which I'll show you pictures later. So these are important. And then also the light blue are kind of like big storm drains. So there's storm drains throughout the area here trying to flow water. And remember, this all has to be done by gravity, because if not, you would have to use a lot of energy to make sure that it's flowing one way. Because imagine poop flowing the other way. Ooh, that makes a mess. So let's take a look at, we're going to look at Tule Ponds first. And this is how we remove pollutants. So
Rain brings pollutants into the area. Here, the soap represents an accumulation of phosphates in the roadways. And when the water comes, it clears the roadways, but brings it to our
So a lot of
habitat.
these are
Is
phosphates.
that good for
now,
our
some
organisms?
plants can take
No.
up phosphates, but if it's too much, then you can start harming our wildlife, which does happen here. Sometimes people dump things that they shouldn't in the middle of the night, and in the morning we'll find something stinky hanging around here. So rain moves pollutants through the watershed, and we need to remove them. So how can you remove them? Before we do that, let's take a look at, these are big storm drains that go out. And these are the ones.
These are the storm drains that when this area gets flooded, water will go out here, prevent flooding for the local community. Now these pipes go throughout the city of Fremont and Newark. And just to show you how
So these are
nice
all underneath
echo.
big cities. Like San Francisco has a lot of storm drains because it's on such a hilly area that they would have too much erosion. So they have to get rid of their rainwater a little bit different than we have in the South Bay, in the East Bay. Now, so what cleans it? Well, it's this little plant, or not little, called Tules. Let's take a look at them. The San Francisco Bay used to have, we've lost about 95% of tules. Tules is a plant that can actually stand a little bit of salt in it. So that's what we call brackish water. And it also thrives in fresh water. Tules were used by the Native Americans for everything from boats to homes to shoes. So this is important. Now, this part here, the reeds itself do not clean the stormwater. It is something in its roots.
Now we're going to look at some of the Tule roots. Tules are noted for its bioremediation. Within the roots, there is lots of fungi that are growing. So art's kind of pulling it out. You see the roots are pretty extensive. And so we're going to take a look at this root as he clears it away. And you could see the roots right there. And those roots have fungi in it that help chelate or take out heavy metals like copper and lead. Oh, and there's a little,
so
a little worm there.
are
yep, little worm.
this kind of plant. And just in case you have a question, is that what happens is it becomes incorporated into the plant, and then it is no longer harmful to humans. So that's what we call chelation. It gets rid of those heavy metals. And where do we get heavy metals? Well, from anything that humans tend to use, like gases. Even we get copper, zinc from our roofs. It's all over. We do lots of little activities where the kids learn about elements and compounds, and which are harmful and which are not. Now I'd like to focus on drinking water. So stormwater can be cleaned naturally, but drinking water, not so quickly. And so in the TriCity area, we, just so you understand, is that we get our water, most of it comes from underground. In this area here, we're blessed with what something is called the Niles cone. It's ancient water, and we know that the water is, some of that water goes back, 5,000 years, where it is underground, and we get 40% of that, and we use it for our drinking water. We also get 40% of our water from the Delta. Now that's from the Sacramento area, where the rivers come into the North San Francisco Bay Estuary. And we get about 20% from Hetch Hetchy, and that we actually buy it from the San Francisco Public Utilities Commission. So our water municipal is called Alameda County water district, which I'll show you a picture of later. Oakland and San Francisco, they all get theirs from different places. So
This is our drinking water. Have you ever looked at the way water comes out at different speeds? Look at how it holds itself and how it goes down the drain. So this is cleaned water, which has gone through an awful lot to get clean, and we're just wasting it down.
yeah, this is just a note to say
to get
that
re-cleaned
it took
again.
a lot for that water to come through. That's why your parents have to pay for water, because it goes through a system to clean it so you do not get sick. And so let's take a look at who cleans it. And it's called, in our area here, it's called the Alameda County Water District. And let's take a look. These are not, this is just one of their areas that cleans Delta water. I've gone through it several times and it is pretty impressive.
This facility, our water treatment plant number 2, uses state-of-the-art technology to treat water from the Delta. As part of a multi-step process, ACWD uses ozone to disinfect the water. We were one of the first agencies in the United States to use that method. All of these different sources of water and cutting-edge technology increase flexibility,
so Alameda County Water District, this is
save
their
customers
plant 2, and it is on Mission Boulevard across from Mission High School, if you've ever wondered what that building was. This is where some of your water comes from. Some of our others come from towers. It's a complicated system of gravity holding some of the cleaned water in tanks above areas, and then through gravity fed through to our homes. Okay, now let's ask the question, where does your poop go? Because that's the one that really causes problem. Our poop, unfortunately, has some bad bacteria in it. Now, there's a lot of things that can't get flushed down, because if they do, that would not make the system work too well. So a little kitty cat there can't be flushed down. But unfortunately, lots of little kids do flush down things. And sometimes parents even try to flush down like small diapers, and that could screw up the system. So again, there's 3 different, in our area here, in TriCity, it is called Union Sanitary District that cleans our poop. And then Oakland and Hayward area, that's East Bay Mud. And San Francisco, that's the San Francisco Public Utilities Commission. So there's lots of agencies, because this is a complicated task.
It's the defining principle of physics here on Earth. It affects nearly everything in the universe and is precisely 9.80665 meters per second squared at sea level. It's also how your poop gets from your toilet to the wastewater treatment plant.
And you see these all around the place. Sometimes when you're going up like 580 near Livermore, you'll see something that looks like this. These are all places that are trying to clean your poop and make products. So let's take a look at this one.
We have to manage our waste because it stinks, it contains deadly bacteria, and it has dangerous chemicals that could affect the environment. You probably know that wastewater gets treated at a wastewater treatment plant, but let's take a look how it gets there. Sewer systems. Urban wastewater systems are needed in densely populated areas so you don't have to deal with your neighbor's waste. In ideal environments, sewer systems are completely gravity-fed, meaning that the pipes slope downward from the source, your toilet, to the wastewater treatment plant. This is done because wastewater has a lot of solids in it.
Because without the gravity fed, then we'd need a lot of electricity to pump it. And we really make too much poop to do that. So Let's take a look at Union Sanitary District in the Tri-City area. Now remember, each area has them. Sometimes you go by them and you don't even notice them because these are our chemists and our people who clean so we can live in this area. When the more people you get, the more poop you get and the more you have to clean.
At Union Sanitary District's wastewater treatment plant, we treat 22 to 24 million gallons of water per day to create safe, clean water.
So if you noticed when it started, it was near Coyote Hill.
Bay.
So this is in Union City. So all the poop from Fremont, Union City, and Newark go to this one area. Then when the water is cleaned, especially the pee, it will go out near the Dunbarton Bridge, or no, it goes into the bay between Dunbarton and the San Mateo Bridge. So just a way where our poop goes. So let's take a look at where these locations are.
In Fremont, Newark, and Union City, more than 800 miles of pipelines bring wastewater to Union Sanitary District's treatment plant. It's here that wastewater begins its real journey, where it's transformed into clean water for the environment, energy to run our plants, and biosolids for beneficial
would be
reuse.
compost. So sometimes when you buy compost, it does have sometimes a human poop component to it. So, and I just want to reiterate, 800 miles of sewer lines. That's a lot, and that's just 3 cities in the Bay Area. And we're, although we're the 4th largest city, Fremont is, think of all the other poop miles out there. Okay, now I'd like to kind of go in, this is a little song called Drippy the Hippie, just so you can understand kind of how this works. Cassie Fries is was a high school student when she wrote this, and this was, her teacher gave her an assignment, and I thought the poem was so cool that we animated it and then added some sounds. So, Drippy the Hippie.
Drippy the Hippie by Cassie Fries, animated by Doris Rayer and Hagos Travolti. This is a little story about a little hippie that goes through the water cycle. I have a very busy life and I'm always on the go. I'm part of the water cycle. It's really cool to know. The gases, hydrogen and oxygen, are what I am made of. I am clean and I'm fresh, and peace is what I love. I am a groovy raindrop. My name is Hippie Drippy. Colorless and tasteless. I'm not your average hippie. I live up in the sky till the clouds turn dark gray, preparing for my trip. I wait for rain each day. I put on my favorite shirt, it's colorful and tie-dye. I wave to the clouds to say to them goodbye. I am a groovy raindrop. My name is Hippie Drippy. Colorless and tasteless. I'm not your average hippie. I fall from the clouds and land in a lake with many other drops. I really precipitate. I vacation here for a while, relax and get some sun. There are many drops who come to the lake for fun. I am a groovy raindrop. My name is Hippy Drippy. Colorless and tasteless, I'm not your average hippie. I swim in the lake and party with the fish. I wait to evaporate. It's the clouds I really miss. As a gas I will rise and travel really high, back to the clouds, up into the sky. Condensation will happen. I'll go back to the state of being a raindrop waiting to precipitate. I am a groovy raindrop. My name is Hippy Drippy. Colorless and tasteless, I'm not your average hippie. I am a groovy raindrop. My name is Hippy Drippy. Colorless and tasteless, I'm not your average hippie.
Okay, guys, so now we're going to go on some activities that you're able to do at home. And then Debbie's going to come on in and show you a whole bunch of things that you can do at home with just a few things. This is Debbie. Hopefully you'll see her.
Hi, everybody.
And we're going to put her full screen as soon as we finish these just few.
Okay. These are just some examples or pictures of how to make a water molecule. So water is kind of unique. If you think about Mickey Mouse ears, we've got one molecule of oxygen and two of hydrogen. So it's the hydrogen that kind of make those ears that stick up. What's really cool about water is that those ears can kind of stretch and move some. Remember how Dr. Joyce was talking about how water holds hands? So that's what allows that surface tension and that movement to happen. Great.
Oh, on this one here, since we were talking how important rain is and how clouds are part of it, if the steam couldn't evaporate and go up and then start condensating, but one of the things the clouds tell us, like it's supposed to rain tonight, and so you want to see if there are these nimbus clouds, so they're gray underneath, and that would tell you they're rain clouds. This kind of cloud, the cirrus cloud, tells you that there's going to be a change of weather, which I think we're having right now. So clouds are actually real important to this whole cycle of rain, and here in California, we always like to have good clouds.
All right, the water cycle wheel. So water's always changing, as you remember from the stories. It's always changing. So as evaporation, precipitation, and condensation, we'll have these listed on the website. You can go and find all these different storybooks and activities. But this just shows you how that hippy dippy, just the one drop, continues to change and move through the cycle.
Okay, so we're going to stop this, so just give me a few seconds to stop sharing on our little Zoom. Okay, Debbie, you are on.
Okay, as usual, we use a lot of different toys to try to look at the different topics that we're studying. This is something we have around here at Tule. Right now, this toy's not doing much. You have to kind of sometimes got to do some work for your toy to make it to work. So this is how we're going to start. I want you to make your prediction, what you think is going to happen. I'll show it to you again in just a little while. I'm just going to turn it over. And here's another one. All right, can you see that? There we go, pretty well. Now if I flip this one over, you can see that pretty well. I'm just going to let that one finish and I'll flip it one more time. You want to make your guesses or your predictions. Now remember, anytime in science when we're making our guess or prediction, you don't go back and change your guess or prediction. That's never wrong. You want to discover, describe, compare, and quantitate. So make your guesses about what you think is happening with this toy and these drops. Let's see if I can get it. I don't know if I'll focus. It'll focus on that. There we go. You can kind of see those drops. All right. Now we've got a bunch of other activities over here for you to do. As usual, it's their activities, the things that you might have around your house. So let's see if we can get started. Come on over this way. All right. We're going to start with just this, just a piece of paper. Yep. Does that work? Okay. I've just got a dark piece of paper and just a small little cup. Small cup is all I needed to be able to find. We're adjusting there. Yeeks. That's good. Okay. Now, I'm going to try to fill this cup up with as much as I possibly can. And this is just plain old water. All right, you ready? Everybody saw that there's not any other drips there now, right? All right. We're going to start pouring some of this in.
I can't see you. You need to go on that side.
Oh, need to go on the other side. Oh. Okay. Need to go on this side?
Yeah, that's good.
Okay. Okay. That's pretty full. Can you get it down on this side? All right. Ray, I want you guys to just tell me, I'll be able to see you a little bit. If you think that this container can't hold any more water, put your hand up like a stop. If you think it can take more water, put your thumb up. If you think this is all the water it can take, put your hand up as stop. If you think it can have more, put your thumbs up. All right, we're going to keep adding a little bit more. This time I'm going to just use this little bit of yellow food coloring and water just so we can see if it can get more. It's a little bit fuller. What do you think? Stop or more? Make your guess. Okay, I see a few of you guessing. Here we go. Oh, look at what's happening. It's starting to bubble up over the top. So what's happening, remember those Mickey Mouse ears? Those Mickey Mouse ears, those hydrogens are the teddy bears. The teddy bear ears are holding hands and they're kind of stretching down. You see how it's bubbling up and over? And you can do this on a penny or any little cup. Now I'm going to keep going until it spills over and it's still going. It's still going. God, did you think surface tension was that strong? Can you guys see the edge of that? So when you're doing this experiment, make sure you get down so that you're level with the top of the container you're doing. Can't take much more. Let's see. Wow, look at that, it's still going. So those are some pretty strong bonds. It still hasn't gone over the edge. Has it gone over the edge over there?
Oh, maybe.
Okay, just on, oh, there we go. We just had a break right there on the top. All right, so you see how much that surface tension, how it moves it around. Now, I do have another couple cups. So as usual with all experiments, you're going to want to do it several times. So again, you can compare your results. You see how I start with it all being dry right there around there so I can see. So again, you can keep track of how many drops or how much water you can measure. That's how we put the numbers into it, quantitate. You can use your words to describe. And again, you will find that the surface tension is a lot higher or stronger than you would think. Now you can compare some other liquids as well. Like if you compare alcohol, dishwashing detergent or dishwashing liquid. Whoa, can you see that? It's still bubbling up and over. It's still all dry. What do you think? Is that all it can take? More, or is it done? Is it going to break? How many more drops? Let's see. 1, 2, 3, 4, 7, 8, 9, 10. Nope, did it break yet? 13, 14, 15, 16, 17, 18, 19, 20. It's gonna go. So from looking at the top, I can tell that the whole side now is covered, like the whole top is even covered. Whoa, do you see that? It was like a big bubble wiggling around. That's pretty cool. So I'll let you do your own experiments at home to figure out if you can, how many drops of water you can get, or you can measure it with beakers, different tools. But again, you can see how it hasn't dropped yet. It's still dry all around. All right, let me move this stuff out of the way for a second. Let me show you another thing to do here as well. All right, so this is just plain old water. Here at Tule Ponds and at Children's Natural History Museum, we have a lot of scientific equipment. So these are just some beakers. Again, they have some measurements on it. At home, you could use your own little measuring cups. And this is just plain old water, and I've added food coloring. Okay? All right, now for this, you can start off with, go that way. Yeah, there we go. Okay, I'm just gonna try it with some, usually you see wax paper. I didn't even have any wax paper, so I'm just gonna use some of this aluminum foil. And this is a little pipette. But you see, just like the top of our last experiment, our water drops like to stick together. So they stick together and make these big bubbles. Now, if you don't have any of these little pipettes or medicine droppers, you can even use something like a straw and just let a little bit out. But what's fun about this is now you can move and stretch these molecules. So I'm just going to use a little toothpick, and I can kind of stretch it around. What do you think is going to happen when blue touches red? Okay, you can make your predictions. Okay, another way to do it is just even on plain white paper. I'll do the same thing. Just going to put a couple dots. And here's some blue. So this is actually an art experiment. Again, we like to discover, describe, compare, and quantitate. So how many, what happens if you put, say, 2 drops of red together with a drop of yellow? Okay, well, you can use a popsicle stick or a toothpick again. So I've got 2 drops here of blue. Let's see what's going to happen. Whoa, 2 became 1. 3 came into 1. So I've got a little drop over here. So you see how this surface tension, again, those water molecules like to be close to each other. So it keeps getting larger and larger with those dots. Now, what happens when we start mixing our colors? Make your guess or your prediction. What's going to happen if I put blue with yellow? Got a guess? Any idea? We get green. What happens if we mix yellow? Did we just do yellow and red? Let's do blue and red. Get a little more red over there. Kind of get a purple. So these are our basic primary colors for pigments, and then we can start mixing and matching. And if you keep track of your experiment, of how many drops you have and all, you'll be able to get all the different colors that you have in your crayon boxes. And that's kind of fun to try to match them up. You can make little mazes for the water drops to go through, all different kinds of experiments. All right, now let me show you something though real quick with this surface tension. I have a little bit of soap on the end of this, oops, on the end of my, so now what's happening to the blob of the water? I have a nice round blob. Oh no. How about this one? So the soap is breaking that bond. It's breaking the surface tension. So instead of these nice bonds holding close hands, now those bonds are breaking. Now let me show you another experiment that might make a little more sense of that. Move these out of the way. So again, just trying to do some basic surface tension experiments. Let me move these over. You can see, hold on just a second. All right, is that good? Can you see there on that corner? Yeah, there we go. All right, so for this experiment, I just grabbed whatever jar I could find or pan I could find. Just wanted something that would hold water. So again, I'm going to pour my beaker of water, just plain old water, into my little pie tin. Now water is fun to play with, it's easy to play with, but again, always make sure you get mom and dad's permission. Okay. Now for this experiment, I'm just using some ground white pepper. You can use regular pepper, you could use Italian seasoning, all kinds of things. Okay, make your guess. What's going to happen when I sprinkle this pepper into the water? Show me with your hands. You think it's going to stay on top? Give me a thumbs up. If you think it's going to sink, give me a thumbs down. If you think the pepper's going to float, stay on top, give me a thumbs up. If you think it's going to sink, thumbs down. All right, ready? Here we go. Well, what's happening? Thumbs up? Looks like it's staying on top. All right, now remember adding just a little bit of soap. Let's see what happens. So what happens is the water molecules are strong enough, they're holding hands strong enough that they are able to hold these pieces of the pepper up. Let's put a drop of soap in. Whoa, what happened there? Just like our other experiment, when we add a little bit of the soap, it breaks that surface tension and caused our pepper to move back through. Now, you may not think that's too important, but remember those videos when we were looking at soaps and all, how anything that runs down the road is going to end up in our stormwater drains. We have a lot of animals here that are the little invertebrates that live on top of the water. Let me move these out of the way so you can see this black tray behind me. Now this is an experiment that's kind of fun. You have to play with it a lot. And again, with the pepper experiment, again, you could do all kinds of spices. Just make sure you have mom and dad's permission. All right, so I've got just a tray of water, and I chose this black container. You can see where I've tried a few paper clips. I'm going to see if we can get a paper clip to float on top of the water, just like I've got one there doing. Now, see, if I just put this right in, it doesn't work. How about if I try it laying down really slow? Nope, that's not it either. How about if I try, I'm going to try a small one. How about if I try using tweezers? That doesn't work either. So you see, you may have to try a lot. I'll give you a couple hints. You may be able to get it to work if you take a paper clip and kind of open it up a little bit. So I've opened that up some. Now if I take a paper clip and I kind of lay it on top, let's see if it'll work. Oh, it worked for a minute. Okay, another thing you can try is try just with a little bit of toilet tissue or tissue paper. So I just put a paper clip on a little bit of toilet paper. Oh, that didn't work either. So you see, just because something's written down in a book, sometimes it doesn't always work. You got to kind of keep working with it. Let's try it one more time using our little tissue here. It's kind of tricky. Again, you have to try a lot. I still have one floating. Let's see if we can get this one to work. Now, see, even with my water though, I can, oh, it still didn't work there. I still have my one floating over here though. And see, I can push the top of the surface of the water and that still will hold it up. But again, what happens if we put just a little drop of soap? Oh, do you see how that moved away? So that's breaking up some of our surface tension there. So again, with this experiment, you can use tweezers, you can use all different kinds of, oh, there it dropped finally. The paper towels, tissue paper, you can try tweezers, all different kinds of paper clips, either the plastic coated ones or the metal ones. But again, once that soap gets in there, the surface tension is broken. So for our small little invertebrates, like our little striders and all, they can't, it messes them up. They don't have their habitat anymore. All right, so now let's move on to the importance of soap. Now with all this stuff that we were using, I was just using regular hand soap and just regular water. Let me move a few of these out so we can get to our bubbles. All right, here's some more water activities you can do. We're now playing with our bubbles. Art's got a fair bit of bubble solution there in the bottom and a handmade little bubble maker. And all our little bubble maker is a straw with some string or some yarn cut through. And I'll show you over here how I've made it while he's playing with that one. Again, I just throw one end of the yarn through here. Because your straw is clear, it's easier to see. And then we're just going to knot it up. You can make this as big or as little as you want. See, all you have to do though is set that down into the bubble solution. Make sure everything is wet. And now you can pull straight up. Sometimes you get a bubble coming off like that. Oh, oh, we almost got a second bubble. Oh, look at the bubbles. Oh, a third little bubble. So now that bubble wave, this surface tension is just wiggling, waggling all over. So again, it's fun to experiment and see how many different kinds of bubbles you get. But you see, you always get a spherical or a round shape once that air pressure equalizes and the surface tension holds it all together. You can see how strong that surface tension is. So again, these are quick experiments that you can do at home. You can try to make different shapes, even with something like a pipe cleaner. You can try to make squares or triangles. We'll see if we can make a triangle here out of this one real quick. So can you get a triangle bubble? Got a triangle shape. No, you still end up with a sphere, a circle. So again, these are all fun things that you can play with at home. Some of you may have some large things like this. Again, the area around the edge of this needs to be all wet as well. So I'm going to spin this around once. You can see that, again, that bubble edge. So again, you guys have fun playing with bubbles. I was going to say. Have fun playing with bubbles. Something like that. Yeah, turn it the other way. Good?
Yes, we have one more, and that's earthquakes. We're going to go to the Earthquake Center in Central Park, and we are going to walk from there. We're going to trace the Hayward Fault all the way to Tule Ponds and learn how Tule Ponds was actually formed. So, and also, guys, we've also figured out how we can allow you guys to come on site. If your parents want to come with up to 10 people, they can email us at our email. Look on our website, msnucleus.org, and you can reserve a time on Tuesday through Saturday. And you guys can stay, your group can stay up to 1 to 2 hours. So you'll be the only family on on site. So that's how we decided to do it, because we couldn't figure out how else to do it. So guys, we'll see you next week, and have fun, and we'll go from there.
Bye,
Thank
guys.
you. Bye-bye.